It is that way. Why that way?
Current leads.
Yes, it leads. Because remember, these are dials that are spinning around like this, so the current is going to be in front. Now, whether IC or IR is longer, I didn't give you enough information, so, at this point, just draw it one way or the other. So that's supposed to be a 90-degree angle right there. So now, the last one, the current from the power supply. Where does that one show up?
You add those two vectors together?
Yep. Well, phasors really, but yes. And so from my drawing right here, I know that the current across the power supply squared is equal to the current from the capacitor squared plus the capacitor squared plus current from the resistor squared. And now bring in my Ohm's law variations. So from this, well, if V equals IR, then I is V over R. Because remember, what I added here, I'm going to rewrite this right here. This is misleading. What I added were the magnitudes there. So this actually should be capital I from the power supply squared is equal to capital I from the capacitor squared plus capital I plus the resistor squared. With the lowercase values, it should be IPS equals IC plus IR. All right, good. Yeah. When you're adding phasors, it's the capital letters, which I did over there correctly. Okay. All right, so now let's exploit our Ohm's law variations. I know for current, I is V over R, so this is V over R. I know the voltages are the same, so I'm just going to use V for it. For capacitance, that's V over X sub C. Squared. And for the power supply, that is V over my impedance. All that squared. Therefore, 1 over Z squared is equal to 1 over X sub C squared plus 1 over R squared. To find Z, I take the square root and the reciprocal in one order or the other. And so Z is 1 over X sub C plus 1 squared plus 1 over R squared square root. And that's the formula for the impedance, for the RC parallel, sorry. Questions to hear before I make it more complicated?
I know you said the formula for impedance is going to be different depending on the circuit.
Yes.
Will it have the same themes, for lack of a better word? Like these are both square roots of the, like R squared.
Probably for any circuit that, now I'm suddenly thinking of loads of bizarre configurations I can come up with. So I hate to generalize that.
Okay.
All right, let's take a quick break, stretch your legs. I have to introduce a new component. called the inductor. And that's gonna require a little bit of running here, so we'll just take a pause, come back. So 225 seems extreme. Then again, somebody did click on one of my videos when they did a search for Japanese hot. All right, so the next component, we're gonna start out, we're gonna call it a solenoid to start with. And a solenoid is just basically, I've got a bunch of wires that are looped really tightly together. So it's just a coil of wires. Now typically if you went out and you, no, we'll keep it like this. All right, so what I want to do is sort of figure out what is the magnetic field that's created. If I have a current flowing in here, so we'll just start out assuming DC current. So I have a current flowing through. We'll stick a battery into it. Current flows through it. And it's really difficult to tell, you know, I just threw a bunch of curls there, so let's be more specific. So let's say that the current is flowing towards us at the top and away from us at the bottom. So if I did a cross section, on the top of it, I have a bunch of wires with current flowing out, and on the bottom, I have a bunch of wire with current flowing away from us. So just wires going like this, and I do a cross section just to take a look at it. What I'm going to do is I'm going to create a Amperian loop. Amperian loop. And there's going to be N wires in there, or actually, let's keep the notation pure. Capital N wires within my loop. This is some length L, this is some distance H. I'm going to start here. Current's coming out this way, so I'm going to go around my loop counterclockwise. So I'm just going to call this A, little b, C, and D. And we're going to exploit Ampere's law. Ampere's law tells us that if we add up the magnetic field times the length all the way around some closed loop, that's going to be equal to U sub naught times the current. That's flowing through the loop. So through loop. So let's deal with the easy one first, the right-hand side. How much current is flowing through the loop? Did I start this up again? I think I did. I did, okay.
What did it say?
It's blinking.
Can't find the patch there.
There it is, okay, yeah. All right, so how much current is flowing through the loop? If I have a current I flowing through the wire, how much is going through that loop?
Zero. I said zero.
Oh, no, there's definitely current flowing through it. Not through it as in the middle. If I got this square here, how much current's flowing in the middle of the loop?
Is it just one before?
In terms of I, how much current's flowing? Piercing the loop, going through the middle of the loop.
Half of I?
Why half?
Because half is going this way, the other half is going.
If we think about current, when current's flowing through it, current's flowing, I is going through every wire. So it would not be half of I.
Yeah, there's same. It'll stay the same.
Through for same as what? Whatever current's flowing through here is also flowing through that, just that's going this way, that's going that way. All right, so how much current's flowing through a wire? Do we need to do numbers? Would that help? Let's say I got 5 amperes flowing through this wire.
So it'd be 5 amperes all the way through.
Okay, so therefore, how much is flowing through this amperian loop?
5.
Not 5.
10.
15.
Well, each wire has 5. I've got N wires. Say it again?
5N.
It'd be 5N in our specific case, or in general, I times N. So this is mu naught I, whatever the current is flowing out of the power supply, times the number of wires I got. All right, the left-hand side. So I got the magnetic field flowing along A times delta L, along A. I've got the magnetic field along B times delta LB. These are dot products. Plus B along C, dot delta LC, plus B along D, dot delta L along D. So if we look at those wires, if I got a wire that's with the current flowing out like that, which way is the magnetic field going to be created? Okay, so I got a magnetic field going like that. Let's put a wire right next to it. So I got a wire right next to it, and it's going to be going in the same counterclockwise direction. So what can you tell me about the magnetic field in between them?
They're opposite directions, so they're going to attract.
They would, that's not, I'm not talking about the attraction of the wires, just talking about the magnetic field. They're opposite directions, so what happens to the magnetic field?
Cancels out.
Yeah. So the magnetic field along this path and this path are close enough to 0. Now I also have wires down here. Outside my loop, but they're still wires nonetheless. What's the direction of the magnetic field created by this green X? So it's going around. So in between here, I have magnetic fields going in the same direction in the middle of it. But if I extend this, because it's not just localized, it does expand, so I've got this green X down here is producing this clockwise magnetic field. The ones up here are doing counterclockwise. So up here, I've got 2 counterclockwise, and I got a clockwise here. Actually, I have a clockwise for every one down here. So there's a weakening of the magnetic field out here. Now, if I've got a really thin solenoid, this drops off to close enough to 0. So the magnetic field outside of an ideal solenoid is 0. So B equals 0 outside. So all I'm left with is the magnetic field in the side. So I have, which is going to be going in that direction, in the same direction as my delta L, because that's the path I'm taking. And so the dot product just is the magnetic field inside times L. that's equal to mu naught in I. If I divide by L, then I have my magnitude of my magnetic field is just equal to mu naught, number of wires over I times I divided by length, or the number of wires per length is basically coil density. And so mu naught, lowercase n times I. So presumably you've seen the video on that. So sorry for the repetition there. This is an ideal solenoid. Ideal solenoid is that if you look at the radius here of the ideal solenoid and the length here, we'll just use big L for that. L is much bigger than R. It's a decent approximation in that case. Questions before we extend this one step further? Yes?
Why does it cancel out for the outside but not the inside?
In the inside, the magnetic fields are all going in the same direction. These are producing ones that are going like that. These are producing ones that go like that. So inside, you get the doubling up of magnetic fields. Other questions? All right, so I'm going to take my solenoid there. I got my power supply, got a switch on it, and then when I connect the switch, what's going to happen? Question?
Current's gonna move through the solenoid.
Okay. So if I have current flow going through the solenoid, it's going from 0 to something. What else happens? What happens when I have a current flowing? All right. So I have a magnetic field that's produced. So if I have a magnetic field that's produced, what else is happening? Pardon? Yes. Because my magnetic field goes from 0 to something, I have a change in the magnetic field. Therefore, I have a change in the magnetic flux. Therefore, I have an induced current. So there's a secondary current that runs along this. There's the primary current coming from the power supply, and then the secondary current created because of the solenoid. Or at this point, it's not called a solenoid anymore, really. It's called an inductor. A solenoid is an inductor, just with higher resistance. So let's figure out what that back current is going to be. I know that the EMF that is created is going to be negative delta magnetic flux over time. I am going to change it slightly. I usually don't write this into the formula, but I am going to treat this is the magnetic flux through one of the coils times N coils. So I'm just going to put a little subscript 1 there, because this is just for one coil times the number of coils, which is just negative N delta B dot A over delta T, which is just negative N big N A delta B over delta T. A is just the area, again, I got this coil of wire, it's just the area of the coil. And my magnetic field is the magnetic field inside it, and we just came up with a formula for that. So my EMF that is produced here is equal to negative NA times the change in U naught in I over delta T. Well, mu naught is the permeability of free space. It's just 4 pi times 10 to the negative 9 in SI units. That's gonna come out. N is just the number of wires in the number of coils I have. That's gonna come out. So I'm left with negative mu naught NA delta I over delta T. Oops, there's a mistake there. Lowercase n. This n, lowercase n, comes out. It is the coil density, it's the number of loops per length, so this would be negative mu naught capital N squared A over the length of the entire solenoid times delta I over delta T. Realize what we have up front there. Mu naught's a constant. These three variables here are just based upon the configuration of the inductor that we have. It's the number of coils, it is the area, and it's how long the solenoid is. This would be a four solenoid because the length, this length is not huge compared to this length, but I mean, it could be treated as a solenoid. So basically, we're looking at something like that. Usually tighter coils. So if I have a solenoid sitting in front of me, well, I have a constant, then I have three things depending upon how the thing is made. This right here is just a constant for a particular solenoid, and this is known as the inductance. And it's symbolized by a capital L.